Okay, we'll start off with a very simple warm-up problem, which is that you are told you have a causal LTI system and that is described by this difference equation. And the first part is determine the system transfer function h of z. So solving that is basically just taking the z transform of the x of the left hand side and the right hand side. So the convention you can use is that yn has a z transform y of z and xn has a z transform x of z. And we know the transfer function is simply given by h of z is y of z over x of z. So we just focus on this difference equation and take the z transform of the left hand and the right hand side, and we get y of z, which is the z transform of y of n. Now the z transform of this term, since z transform is linear, is 3 by 2. The z transform of yn minus 1, that just creates, that's a shift, so that adds a multiple z to the minus 1 times y of z. Plus the z transform of this term is, again, you just have a time shift, so that's z to the minus 2 y of z. And finally, the z transform of this thing is you have a shift in x by 1, so you get z to the minus 1 x of z. Now you collect all the y terms on the one side, the x terms on the other side. So you bring in the y terms on the left hand side equal to z to the minus 1 x of z. And finally, you simply take y of z common, you get 1 minus 3 half z inverse minus z to the minus 2 equals to z inverse x of z. And finally, I cross multiply, bring x of z to the left side, so I get y of z over x of z. That is simply equal to z to the minus 1 over 1 minus 3 half z inverse minus z minus 2. So that is your transfer function, and that solves the first part of this problem. Okay, the second part asks us to plot the poles and zeros of h of z. So our h of z in part 1 we got z inverse over 1 minus 3 half z inverse minus z to the minus 2. Now to compute the poles and zeros, we need to write, the best way is we write it down in terms of factorized forms, where each factor is the form 1 minus a z inverse. So the numerator is already factored. We need to do the factorization of the denominator, and that's just the quadratic formula. So the roots of 1 minus 3 by 2 z inverse minus z to the minus 2, they are simply given by, there are two roots, minus b plus minus b squared minus 4ac over 2a, where a equals to 1, b equals to minus 3 by 2, and c equals to minus 1. So you just plug that in and you get your roots to be 3 halves plus minus, that's 9 by 4 minus 4 times 1 times minus 1, that's plus 4 over 2 times 1, that's 2. So you get 3 halves plus minus 4, 9 plus 16 over 2, That's 3 halves plus minus 25 by 4 over 2. And you finally do the calculation. It ends up being 3 by 4 plus minus 5 by 2 times 2, that's 5 by 10. Okay. So you get 3 by 4s plus minus 5 by 4. So 3 by 4s plus 5 by 4s, that's 8 by 4s is one root. And the second root is 3 by 4 minus 5 by 4, that's minus 2 by 4. So that's 2 and that's minus 1 half. Right? So again, something that you have done many times, just a revision. So it's z to the minus 1 and one root is, so I get 1 plus 2 by 4 z inverse. And the second root is 1 minus 1 half, so 1 plus 1 half z inverse. Sorry, 1, this is 1 root is 2, so 1 minus 2 z inverse. Okay. So the question is asking plot the poles and zeros, and we now know that we have a pole at z equal to 2, and we have a pole at z equal to minus 1 half. Right? So these are the two poles that we have gotten. And we can simply plot them. So z equal to 2 is here, z equal to 2 is here, and z equal to minus 1 half is here. If I multiply h of z on the top and bottom by z squared, so I get z over z squared minus 3 half z minus 1. Okay. Now if you look at this, you see that you have a 0 at z equal to 0. So that's the pole 0 diagram that you'll get. Okay, let's move on to the second question, and this is really a straightforward question, assuming that you know or remember details about linear phase systems. So the question is, determine which of the following systems described by their impulse responses. So each of these plots is Hn. Okay, these are all Hn, A, B, C, D, and it is asking which of these following systems described by their impulse responses are not linear phase systems. Now, the first thing you can look at these impulse responses and tell is that among the two major classes of systems or impulse responses, which are FIR, finite impulse response, and IIR, infinite impulse response, what type are these? So these are all FIR filters. They are all FIR systems. And linear phase FIR systems, we studied 4 types of them: type 1, type 2, type 3, type 4. And we saw their characteristics. So this is a really simple question if you remember those details. What is part A a linear phase system or not? Right, so this is a linear phase system, and the way we say that is we have n equal to 3, that is the length of the filter. This means that m equal to 2, and this filter is symmetric about about m by 2 equal to 1. So what kind of a filter is this? Is this a type 1, 2, 3, 4? What kind of a filter is this? This is a type 1 filter. Okay. Odd length and symmetric about the middle, m by 2. So this is a type 1 filter and this is linear phase. Let's come to B part. Is this linear phase or not? So this is not a linear phase system, because if you remember all the 4 types of the filters, they have to be either symmetric or anti-symmetric. So this is neither symmetric nor anti-symmetric. Okay. So we'll have to verify other things where it is symmetric about, but just looking at this, you can see that this is not a linear phase system because it's not symmetric. Let's come to part 3. This looks like symmetric. So now we have to verify the other details. It's n equal to 3. Again, this means m equal to 2. And this is symmetric about m by 2 equal to 1. So this is a type 1 filter and this is a linear phase filter. Let's go to the last part. Is this linear phase or not? Yes, this is linear phase. Now which type it is? So n equal to 2. So n is equal to 2. This means that m equal to 1. This means this is symmetric about 1/2. So what kind of a filter is this? This is a type 2 filter. Okay, let's go to the last type. Is this linear phase or not? This is linear phase, but this is anti-symmetric. Right? So we have n equal to 3. This means m equal to 2, and this is anti-symmetric about 1. So what kind of a filter is this? So this is type 3 FIR filter. Okay, let's move to the third problem, which is again a simple problem if you know your facts about linear phase systems which have real valued coefficients. So the question is saying which of the following systems are linear phase systems implementable using real valued coefficients. Okay. Now, the first thing, these pole zero diagrams are just omitting the trivial poles at z equal to 0. So if you just look at these diagrams, what kind of filters are these? Are these FIR filters or IIR filters? These are all diagrams of FIR filters because an FIR filter has no non-trivial pole. Okay, an FIR filter is always given by, an FIR filter has only the form, if you assume causal FIR filter, it is A0 plus A1Z inverse plus A2Z to the minus 2 plus AMZ to the minus M. It has no denominator polynomial, and poles correspond to the roots of the denominator polynomial. Sometimes you will see FIR filters written as numerator and denominator polynomials, but what really happens is there is a pole zero cancellation. Okay, so the thing that distinguishes FIR filter from IIR filter in the pole zero diagram is that an FIR filter has no pole other than at z equal to 0 or z equal to infinity. So it has no non-trivial pole. Okay? So I'll just repeat this fact that an FIR filter, if it has poles at anything besides z equal to 0 or z equal to infinity, it is not an FIR filter. And a causal FIR filter only has poles at z equal to 0. If I put a pole of fourth order, which is the same as the number of zeros, then this is a causal FIR filter. Okay. Okay, so let's go back to the original question then, which is that these are linear phase. Now we know that these are FIR systems and they have real valued coefficients. The question is, which one of these diagrams correspond to linear phase real valued coefficient? So what about part A? So yes, this is a linear phase FIR filter, and the reason is that with real coefficients, and the reason is that if you have linear phase, then you always have the zeros satisfy the relation that if z1 is a 0, this implies that z1 to the minus 1 is a 0. So if this is a 0, then this had to be a 0. And the real valued coefficients mean that the zeros occur in conjugate pairs. So this had to be a 0 and this had to be a 0. Okay. So for every 1 0 which is not on the unit circle, you get 3 more zeros, and these zeros satisfy those relationship. So you declare that this is a linear phase FIR filter with real coefficients. Now what about part B? So this is not a linear phase FIR filter because this 0 does not have a 0 at this location. And similarly, this 0 does not have a 0 at this location, and the conjugation, either one of those reasons, it's neither linear phase nor real valued coefficients. What about part C? Is this, so this is in linear phase with real valued coefficients. All the zeros are real valued, so there is no issue of conjugation. And this one and this one, they are sort of the inverses of each other, so they give you the linear phase, and the inverse of this is exactly the same, so you only have 3 zeros, and they satisfy the relationship. So this is a linear phase filter with real valued coefficients. Okay, let's move on to the next problem. It says a linear phase FIR system has this Z transform, and its impulse response has unit energy. A is greater than or equal to 0, and these conditions are satisfied. And it says determine the impulse response Hn. You are not given A, B, and C. You are supposed to find those. Okay? So start with 1, H of Z equal to A plus BZ inverse plus CZ to the minus 2. The degree of this polynomial is 2. This means that the length of this filter is 3. Okay. Now, this is a linear phase FIR system, and you have length equal to odd. So it's either a type 1 filter or it's a type 3 filter. Okay? Now, the other question, the other aspect you are told is that h of e to the j pi equal to h of e to the j0, they are both equal to 0. So you have if I draw a pole zero diagram, you have a 0 at 0, z equal to 0, and you have a 0 at z equal to -1. That is what this condition means. Now, you are only left with two conditions, type 1 filter, type 3 filter, and you have a 0 at z equal to 1 and 0 at z equal to -1. Which of these two types can this filter really be? Do we have an even number of zeros at z equal to 1 and z equal to -1, or odd number of zeros? We have an odd number of zeros at each one of these locations. Okay, we have 1 0 at z equal to 1, 1 0 at z equal to -1. So this is what differentiates type 3 from type 1. So this is a type 3 filter. If this is a type 3 filter, then we can now try to start unraveling the mystery of what should A, B, and C be. And a type 3 filter is anti-symmetric about the middle. So a type 3 filter will be at 0, 1, 2. This is length 3. So a type 3 filter is anti-symmetric, which means that the sample at 1 is 0, guaranteed. And whatever is the sample here, at 3, it's the negative of that. So this means that my B for type 3 filter has to be equal to 0. And my C is related to my A. How? My C is equal to -A. Okay. So, because remember, I can just read off the filter coefficients by looking at these coefficients of my Z transform. Okay, this is my H of 0. This is my H of 1. This is my H of 2. So, since it's anti-symmetric, my middle part has to be 0. So now my H of Z is simply A plus minus AZ to the -2, which means that my HN is simply equal to A0 minus A. We still haven't figured out the complete impulse response. We need to find the value of A, and what we are told is the impulse response has unit energy, which means that A squared plus A squared equals to 1. So the energy of this means that H0 squared plus H1 squared plus H2 squared, this is equal to 1. So this means that 2A squared equal to 1 and A equal to plus minus 1 over square root of 2. Now we are told that A is greater than or equal to 0. So this means that A is actually equal to square root of 1/2. So my impulse response is Hn equal to 1 over square root of 2, 0 minus 1 over square root of 2. Okay. The second part of this question asks you to compute the absolute value of the frequency response, and that's trivial. You just use the definition of the discrete time Fourier transform. So I'll leave that as an exercise because we have other practice problems to do. It's just a 3-length filter. Finding the discrete time Fourier transform is really a piece of cake. Okay, this is a question which says we have a length 5 FIR filter which has this frequency response, and we are given some facts about this filter, and we are asked to determine Hn. Okay, so the first fact we are given is that minus pi to pi h of e to the j omega d omega is 4 pi. Now, it's again sort of slowly unraveling the mystery. It's a length 5 FIR filter. AHN has 5 elements. Okay. And 1, 2, 3, 4, 5. First of all, we don't know where the filter is starting from. But if we come to second condition, so this is the first condition we are given. Let's come to the second condition. H of e to the j omega is a times e to the j omega e to the minus j2 omega, with this a being a real and even function of omega. What does this mean? This means that h of e to the j omega, this is a linear phase filter. Right? It's getting multiplied with a, which is just a real function, so it can be either positive or negative, times e to the minus j2 omega. So from 2, we know that h of n is linear phase. Now the condition is n equal to 5 and we have linear phase. So that means we are either dealing with type 1 or type 3 filter. Okay. And regardless of that, if we have 5 quantities, we actually have to determine only 3. Why? Because whether it's type 1 or type 3, it's either symmetric or antisymmetric. So instead of 5 numbers, we are dealing with only 3 numbers. And so we'll just call this h of 0, h of 1, h of 2, h of 3, and h of 4. And let's try to slowly find out if we can, using these other facts, we can determine these other values. So what about h of 0? If you look at this, the first condition, even though it may look like you can't use it, the first condition is related to the fact that your inverse dTFT formula is given by 1 over 2 pi minus pi to pi h of e to the j omega, e to the j omega, and d omega. Okay. So we are given that minus pi to pi h of e to the j omega d omega equals 4 pi. If I plug n equal to 0 here, I get 1. So this means that h of 0 is simply equal to 1 over 2 pi minus pi to pi h of e to the j omega d omega. Okay. Now you are given this quantity. This is equal to 4 pi. So this means this is given to be 4 pi. So I get h of 0 equal to 4 pi over 2 pi, that is equal to 2. So I've determined at least the first coefficient of my impulse response. Now let's come to condition 3 and let's try to find out what does that tell us. So what that tells us is that a of e to the j0 is 8. This means that h of e to the j0 is not equal to 0. Because that you have the value there is simply 8. Okay. This is equal to 8, so it is not equal to 0. And also h of e to the j pi is not equal to 0. So we don't have a 0 at z equal to 1 and z equal to minus 1. That means what kind of a filter among the two types that we have, type 1 and type 3, which filter do we have here? We have a type 1 filter because type 3 filter always has zeros at z equal to 1 and z equal to minus 1. So this is a type 1 filter. So this means that our impulse response is really h of 0, h of 1, h of 2, and then h of 1 and h of 0. Okay. So we have found h of 0, we need to find these other two values. Okay, now we simply use, so I'll call these numbers to make it easy. I'll make it A, B, C, A, B, and A. B and A. Okay. So we have already found A, that is 2, and so we are left with finding two other numbers. So I have h of e to the j omega, that is simply equal to n from 0 to 4, h of n e to the minus j omega n, that is equal to, just going to plug that in, that's 2 times e to the minus j omega n plus that's 2 times e to the minus j omega 0 plus b times e to the minus j omega plus c times e to the minus j 2 omega plus b times e to the minus j 3 omega plus 2 times e to the minus j 4 omega. Okay. So that's equal to 2 plus b e to the minus j omega plus c e to the minus j 2 omega plus b e to the minus j 3 omega plus 2 e to the minus j 4 omega. Okay. Now, from condition 2, we know that h of e to the j omega is equal to a e to the j omega e to the minus j 2 omega. So I just want to write it in this form. I just want to express this in this form, and to do that I'll just take the e to the minus j 2 omega common, so I'll get 2 times e to the j 2 omega plus b times e to the j omega plus c plus b times e to the minus j omega plus 2 times e to the minus j 2 omega times e to the minus j 2 omega. So I've just taken this constant, and now I can write things using the Euler's identity. I have 2 common, e to the j 2 omega plus e to the minus j 2 omega plus c plus b times e to the j omega plus e to the minus j omega e to the minus j 2 omega. Okay. And that is simply 2 times 2 cosine of 2 omega plus c plus b times 2 cosine of omega e to the minus j omega. Okay. So I have now simplified it as much as I can, and now I go back and I use these two facts. A of e to the j0 is 8 and a of e to the j pi is 12. So I have found this to be my A of e to the j omega. Right? And we are told that A of e to the j0 is 8. So I just plug that in. This means that 2 times 2 plus c plus b times 2 equal to 8. And that means that 2b plus c equal to 8 minus 4, that's 4. So I have one equation from here. And then the next condition I have is A of e to the j pi is 12. So I have A of e to the j pi is 12, and I plug that in. I get 2 times 2 cosine of 2 pi, that is 2 plus c plus b times 2 times cosine of pi is minus 1. So I get minus 1 equal to 12, and I get c minus 2b equal to 12 minus 4, that is 8. Okay. This is the other equation, and hopefully we know how to solve two equations in two unknowns, and that will give us the value of c and b. So the main trick we have used here is pretty much just use our knowledge of the filters. We said it's length 5, so, and from condition 2 we determine it's a linear phase. That means it's either type 1 or type 3. Then from condition 3 we figured out that it does not have zeros at z equal to 1 and minus 1, so it has to be type 1. Then we figured out h0, and after that we just wrote h of e to the j omega in this form to be able to use the other two pieces of information to solve the other two unknowns. Before we run out of time, I want to just discuss problem 7 first before I go to problem 6, because problem 7 is a really simple problem. You are given this pole zero diagram. You have a sixth order pole at 0, and you have these 6 zeros. The first question that is asked is this an IIR or an FIR system? And we already had this discussion. So this has no poles other than at z equal to 0. So this is actually a causal FIR filter. Okay. And of course, this has 6 zeros. This means that the length of the filter is 7. Okay. Now, it asks, just looking at this pole zero diagram, what kind of a filter is this system? Is it low pass, high pass, band stop, or some other type that you recognize? And you're only looking at the zeros, and the angle that the first zero makes is pi by 3. The second zero makes an angle of 2 pi by 3. And they are pretty much symmetric around the positive and negative frequencies. So what kind of a filter is this? This has 3 zeros in the omega equal to pi by 3, omega equal to pi by 2, and omega equal to 2 pi by 3 region, and similarly in the negative side. So if you think of it, it is hitting zeros at omega equal to pi by 3, then pi by 2, then 2 pi by 3, and then it's going back up. Okay. This filter, if I just plot the zero frequency from 0 to pi, okay, this filter you will characterize as a band stop filter. It is attenuating the frequencies between pi by 3 and 2 pi by 3, or a little before pi by 3. So just looking at the shape of the filter, you can determine that it's a band stop filter, and you can try to roughly guess the shape of this frequency response. And of course, you will have exactly the same kind of shape on the negative side. Okay, so this is what your h of e to the j omega will look like. Okay, this is a little bit involved question. We'll see how far we go in the remaining time. So we are given that it's a real valued linear phase FIR filter, and this is what the system transfer function is, and it is known that h of e to the j omega equal to 0 for omega equal to 0. And the first question that is asked is, what is the length of the filter? So that is easy to answer. N equal to 6, because we have a polynomial of order 5. We have 5 zeros. It is already in the factored form, so we know that it's a length 6 filter. The second question is also rather easy. What is the type of the FIR filter? So n equal to 6, which means that it's either type 2 or type 4 FIR filter. Now we are given that it has a 0 at omega equal to 0. So since it has a 0 at z equal to 1 and it's only 1 0, we are going to say that this is a type 4 FIR filter, which means that HN is antisymmetric. Part C is, what is the group delay of the filter? Now, we had talked about that a linear phase filter always have the phase of this is always of the type e to the we can write that as h. We have the magnitude times e to the j m by 2 omega plus some alpha factor. Okay, so a linear phase filter's group delay is given by, if you remember the definition of the group delay, it's e to the minus j m by 2 omega. So the definition of group delay is minus d theta omega by d omega. So that is equal to m by 2. So m in our case is 5. So our group delay is 2.5. Now the last part is determine the locations of the unknown zeros of the system. So we are given that we have a 0 at omega equal to 0. We have a 0 at e to the j pi by 2 at these locations, and a, b, and c are unknown. Okay, so we'll try to find the locations of these zeros. So let's find out first what are the zeros that we know about. We have a 0 at z equal to 1. We have a 0 at e to the j pi by 2. So we have a 0 here. And we have a 0 at z equal to 0.5. So we have a 0 at this location. And we are asked to find a, b, and c. Now remember that this is a linear phase filter. Okay. So we ought to be able to use that information to find the other zeros. So if I have a 0 at 0.5, Because of the linear phase condition, that should give me another 0 at which location? Okay. So I'll get a 0 at z equal to 2. If I have a 0 at z equal to e to the j pi by 2, where else should I have a 0? So I get another 0 at z equal to e to the minus j pi by 2. So that gives me 1, 2, 3, 4, 5 zeros. Okay, we had 5 zeros and we have found the 5 zeros. So uh, we have the zeros were there. It had n equal to 6, so it had 5 zeros, and we have found the 5 zeros. This 0 is 1, 2, 3, 4, and 5, and that completes the number of zeros that we needed to find.